Hi, my name is Naveen, and today I'm going to be talking about lab number 2 for Physics 2212. So, introduction. The purpose of this lab was to explore the distribution of electrical charge across floating tapes along the floating tapes lab conducted 2 weeks ago. A model was created to treat the charges on the tape as evenly distributed across the tape. The model we used the last week for the lab treated both tapes as a singular point charge, and this was slightly inaccurate. So the physics principles involved were Coulomb's law, the law of conservation of charge, and Newton's law of gravitation. Floating experiment observations. So both tapes were 7.8 inches approximately, so that's that amount of meters. And then using the constant given in lab 1, I can estimate the mass to be about 0.0001912 kilograms. And then the distance between the pieces when the tape started to float was 0.034 meters. So using this data, I can do a couple things. I can, one, find the gravitational force acting on the top tape. That's about that many newtons. And we know that the electrical force is equal to the gravitational force because the top tape is at rest. So the two forces must equal. So the model. First, I inputted my value for the mass of one tape, which is just something I got by using the approximate length of the tape. The value for Q is what I tampered with until gravitational and electrical force were equal. My initial Q value was too small. I used 1.579 times 10 to the negative 8th coulombs. That's the value I got from lab 1. So in this model, we ignored air resistance and assumed there was an even amount of charge on both tapes. Model continued. So this was the helper function that I used to find the E field at certain observation locations from a given point charge. You just find R by subtracting the observation location from the position of the charged particle, and then find the magnitude of R by just using the function mag parentheses R, or close parentheses. And then R norm, that's the normalized vector of R, that's just the unit vector, R hat. So then you just find E by using the formula KQ over mag of R squared times the unit vector R hat. And then the helper function returns the electrical field. Now, next I changed the position of the top tape to reflect the position of the top tape when it was at rest over the bottom tape. So that's just 0.034 meters above the bottom tape. That's what I measured. Model continued, so I modified the E scale and F scale. That's just to adjust arrow sizes. Nothing too major there, but the big thing I did inside the for loops was I modified the E field update and force update formulas. So that's Fe on dq top by dq bottom. I just set that formula equal to dq top dot charge times dE at dq top by dq bottom. What that does is it finds the force on the dq we're considering on the top tape, and it finds the force on that due to one of the charges on the bottom tape. So yeah. And next, I just update the FE arrow and FG arrow formulas. I just change the axis values to reflect the electric force and gravitational force. Conclusion. So what if you had modeled each of your tapes as a single point charge like in the previous lab? So in the last lab, when I modeled the tapes as point charges, the value I obtained for a charge on a single tape was 1.579 times 10 to the negative 8th coulombs. And in this lab, the value I got was 2.9611 times 10 to the negative 8th coulombs. Why do these estimates differ? Which value is more likely to be closer to the real value, and why? The estimates differ because the electrical field interaction between the tapes means some of the force is directed in horizontal directions. So if you take the leftmost charge on the top tape, it's experiencing a horizontal force from the rightmost charge on the bottom tape, and the horizontal force is pointing to the left. But the horizontal forces all cancel out because for every force that the top charge on the left feels, there's also force on the top charge on the right that is in the opposite direction. So all the horizontal forces cancel out on the top tape. But when you treat both tapes as point charges, these horizontal components of the electrical force are ignored, and you get a less accurate model of the distribution of the charges in the floating tape lab. So the model used in this lab, the one that treats the charges as evenly distributed across the tape. That model is probably more accurate because it more accurately models the distribution of the charges in the tape. However, the model used in this lab is not perfect. The model in the lab assumes all the charges are distributed perfectly along the tape, which may not be true because of electrical imbalances in the surrounding environment, which may cause polarization. It also assumes that there is an even amount of charge on both tapes, which is not necessarily true.